Thank you very much, Luke. Pleasure to be here. This image is part of a mosaic of 7,500 Hubble exposures. This deep view of our universe contains hundreds of thousands of galaxies, stretching back 13.3 billion years to only 500 million years after the Big Bang. Can you believe that up until the 16th century, we thought that we were at the center of the universe, the geocentric model? That then got thrown out for Copernicus's heliocentric model of the universe. Copernicus formed the philosophical idea that the Earth should not be at any central or special place in the cosmos. This then became known as the Copernican principle. Observations that we make from Earth should be representative of observations from any point in the universe, any random point. And the laws of physics should be the same everywhere. When extended to cosmology, this then became known as the cosmological principle. The idea that if we look out into the universe, we should see it being the same everywhere, being homogeneous, and looking the same in all directions, being isotropic. This assumes homogeneity and isotropy. And we went all in on these assumptions. From them, we derived the Freeler-Lemaître-Robertson-Walker metric that we use to describe our universe. And inside of it, the scale factor A that governs the expansion of the universe assumes isotropic expansion in a homogeneous universe. And from this, we then built lambda CDM. Lambda for dark energy and CDM for cold dark matter. This is our standard concordance model of cosmology today. But what if we went all in on an incorrect assumption? In this talk, I'm first going to start with the cosmic dipole, this kind of tension in cosmology that you may not have heard of before. And then I'll talk about how that relates to the current day, the state of the field, and cutting edge techniques with Bayesian statistics that we can use to probe this tension. I'll then let you know what we found and why it's interesting, and what that can tell us about the future and the next steps that we need to take. So firstly, this is going to be talking about the cosmological principle, as I mentioned before. And one of the biggest pieces of evidence that supports that is the cosmic microwave background. This is radiation from the very early universe, only a few 100,000 years after the Big Bang. And when we look at it, these temperature fluctuations between the yellow, red, and blue, they're very tiny. You can see it's of scale 10 to negative 5. So when we look at this, we see that it's pretty smooth. It looking pretty much the same way everywhere tells us that the universe today might also be the same. Because these small perturbations in the early universe would have then grown by gravitational instability to give us that large-scale structure today. And that's why we think one can map to the other, and that the cosmological principle seems to be a model that holds here. Now, when this CMB comes to us, well, we're not just an observer standing still, we are moving through the cosmos. So we actually see this sky being Doppler shifted. In one direction, it's redder, the other direction, it's bluer. This is the higher temperature, the lower temperature. And if you work backwards, you can infer that we might be moving at around 370 kilometers per second towards some location in galactic coordinates. Now, this is just theory of our frame versus the cosmic rest frame, which is the cosmic rest frame being the frame which you see the CMB as being maximally isotropic, maximally looking the same everywhere. And this is absolutely fine. But that means that if we want to look into other things in the universe, like let's say we're counting the number of galaxies or certain type of object around us, we should firstly see, according to the cosmological principle, that we have a smooth distribution of them. They look pretty much the same way everywhere on the sky. And there should be also a kinematic dipole imprinted on it from our motion. It should be nice and smooth, and our motion should cause that same thing as the CMB. So in a sense, the CMB is our control here, and we can look at other things to see, does it hold for different objects? And can we test that large-scale structure, large-scale distribution? Now, what our movement is going to do for how objects change and move on the sky is firstly going to be a relativistic aberration. This is where an object is at a certain angle towards us, and when we're moving towards a certain direction, that angle will shift and become slightly tighter, slightly smaller angle. Now, when you're looking at lots of objects in the sky at the same time, this becomes a little bit more clear. Here, I've divided the sky into equal area pixels that are comically big right here. The different colors just tell you it's a different pixel. And if I'm assuming that everything is homogeneous and nice, like the cosmological principle, I'm going to imagine that I have the same number of sources in every pixel. Here I've put 4 in each pixel, and I'm just focusing on the center ones because it's easier than putting them all over the map. And if we start moving towards the very center of that map right there, because of relativistic aberration, we're going to see those sources move closer and closer and closer together. So if we're looking at the density of objects, the number of them per pixel, and that density should change across the sky, and we can infer that our motion might be a cause of that. So that is the first effect. Now also, I mentioned before a Doppler shift, and we're going to get the same Doppler shift looking at the number of sources around us. So when we have our catalog of objects, they will have a certain flux density, a brightness at a frequency. And what this plot here is telling us in log-log space is that objects that are really bright towards this end of the plot, there's not many of them. And objects that are much fainter, well, we have a lot of sources that are very faint. Now, with your catalog, you're never going to include all objects at the same time. Your catalog has a certain completeness limit or other limits that you want to impose. So we are going to do the regular thing and impose a flux density limit right there. Objects in the shaded region, we don't include. And objects above that, we do. And putting this flux density limit is what causes an interesting effect for the dipole. Because objects that are in this shaded region that should not be included, well, in the direction of our motion, they're getting blue shifted. They're getting brighter. So they'll get actually boosted in to our survey. In the opposite direction where we're coming from, the anti-direction, objects are going to get boosted out of our survey when they should have been included. So that means not only do you have the clustering from relativistic aberration, but you're actually detecting more in front and detecting less behind. So you can put all of this together to give you one, and I'm not going to show too many equations today, but this gives you one nice equation for the dipole. You put it all together, reasonable values of x, which is that slope from before, alpha, which is the relationship between the flux density and the frequency, and then put in a nice value for velocity. Let's say 370 kilometers per second, like the CMB. What you get is that this turns out to be a very small effect across the sky, a 0.1% modulation. This means that hypothetically, if I had about 1,000 sources in every single pixel, then at the poles, where this effect is the strongest, I'm expecting plus or minus 1 source. So we've set ourselves up with quite a tight problem to work out here. And people have also dealt with this problem in the past. But first, I want to recap how this relates to cosmology, because we've talked about dipoles and how source counts change. So I want to really hammer in that we can see how the density of objects changes across the sky, like galaxies and radio sources. And then we can infer a velocity from that. And if it disagrees with the CMB, then we have a problem. This would mean that something else is causing the distribution of those objects and those source counts to change. That could be systematic. It could be something else that we don't understand. It could be higher order signals. But it could also tell us that these objects that we're looking at are not distributed homogeneously in our structure. That perhaps there is some kind of cracks in ΛCDM in the standard concordance model. And any anisotropy would violate the cosmological principle. Now, throughout the literature, people have done this test. Over about 40-ish years it's been theorized. We've had good data to do it in around the last 20, 25 years with NVSS. I'll explain these two surveys later on in more detail, but for now, they're just radio source counts. And this is the direction of dipole that people typically get. And within these 2 sigma contours going all the way out, you can see that the CMB star for reference, they about agree within 2 sigma. So the dipoles that we infer, they're in the right quadrant on the sky, and there's not a lot of tension there. This gives us confidence. But when people look at the amplitude of the dipole, they consistently find that it exceeds the CMB expectation. We'd like it to line up with that nice gray line at 1 times the CMB amplitude, but consistently across radio, optical, and infrared, we find that it's instead 2 to 3 times the expectation. So if you assume that it is just an effect of our motion, this is saying that we're moving at what, 800 or 1,000 kilometers per second instead of the canonical 370. So there's some disagreement here. And this problem over time has indeed gotten worse. You can see in recent times, the citation count is going up as more people are dealing with this problem. And you can kind of see a very brief history of NVSS. People think it's okay, more data coming out, the problem's getting worse, the tensions are getting higher. And now it is at the point where it's about a 5 sigma tension, higher than that for some data sets as well. And we like to think about our sigmas of tension. You might have seen other things report this report, like Hubble tension. That's also been reported around the 5 sigma. And Hubble tension gets a lot more coverage. There's many people working on it. But earlier this year, when I went to the Cosmoverse conference, which was one about tensions in cosmology specifically, there was a lot of conversations about Hubble. That pretty much took the entire stage. It was just me and one other person talking about the dipole. And there's a lot of interest in this because if anything, this tension might be more fundamental. The Hubble tension tells us that there's a problem in our current model of the universe. These measurements of the expansion are disagreeing with different data sets. Whereas the dipole tension tells us that universe model might be wrong to begin with. It might not be Friedmann at all. And in those kind of frameworks that would not be Friedmann, the Hubble tension doesn't even exist. The Hubble parameter is this concept that only exists in this one model. So that's something to think about here. And this challenge does now pose a significant challenge to the standard model of cosmology. Now, because we're talking about tensions a lot today, it's important to make sure we're all in the same playing field here. Essentially, higher the sigma, higher the tension. And a tension is this disagreement between two concepts. Usually it's observation and theory. There can also be different models and different theories as well. And I like to imagine that they are pulling against each other, these two ideas. The good thing about this is it tells us where the cracks are in our understanding and can lead us to find new physics, new ideas. One classic example is the orbit of Mercury. For ages, they tried to explain that with Newtonian gravity. And that, in a sense, they probably didn't call it that at the time, but that was a tension. And then came along general relativity that then resolved that tension. Now, again, we're talking about sigmas, so I very much want to make sure we're on the same page here. This is just for students to understand. Professors are very familiar with this. Now, we have a standard Gaussian distribution with a mean at the middle. And within plus or minus 1 of that mean, we have the 1 sigma range. What this tells me is that if I'm drawing some sample from this distribution, 68% of the time, it's going to fall within that 1 sigma bound. If I extend that to 2 sigma, that is then 95% of the time, 3 sigma, 99.7% of the time, falling in that range. An equivalent statement would be something falling on those bounds or outside of it is then only a 0.3% chance. So when people are talking about a 4 sigma tension or 5 sigma tension, they're saying that this event is so rare that these two ideas or data sets should only be this discrepant that percent of the time. It's a nice way to convey probabilities. And when we're talking about 5 sigma tensions, that is a 1 in 1.75 million chance. So they're saying this should not happen, therefore it is interesting we report those numbers. Now, with the units of tension quantified, we can talk about the 3 main pillars. You can have a tension between parameters. This is where you have some expectation. Let's say we are expecting the CMB velocity, right? Then you get your inference, which is some hysteria curve. You have your measurement, some error, making some measurement there. And you can compare that to a known value and see, oh, that's so many standard deviations away from the curve. I'm going to infer some amount of tension. It's in how far away it is. So that's tension between parameters, but that is a frequentist interpretation of that. Another one, maybe moving towards Bayesian statistics, would be a tension between models. You can get one model and test it for your data, and you'll get an evidence for your model given your data, the probability of observing it. You can do it for another model. And then you get 2 evidences, and you can stack them side by side. On top of each other gives you a Bayes factor, a betting odds ratio between which model you would put your money in. And that is, in a sense, a sign that can quantify tension. And the third pillar is quite a new one. This is tension between data sets themselves. Here, you no longer care about the parameters. And here, you're testing one model. And what you're doing is you're saying, do the same data sets, so different data sets make the same predictions on that model. You're looking at just one pillar now. And for the dipole, this hasn't been done, and that's what we do here. Now, when we're quantifying the tension between data sets, we have what I said before, which is the Bayesian evidence. This is ZA. It's probably observing your data for your model. What we do is with our 2 data sets A and B, we compute ZA, probably observing A, ZB, probability of observing B. And then instead of looking at them individually, we put the data sets in the same room together and say, okay, what's the probability of observing both of them at the same time? And you could compute these with nested sampling or Monte Carlo algorithms. It's just about doing an integral in a fast way. And then you put these evidences together and you stack them on top of each other. And this forms something called the R statistic. And this is a really powerful probe and has a lot of applications. The first thing to note is that because it's a ratio of evidences, this is technically also a Bayes factor. But what I want to instead talk about is the interpretation. These two data sets on the bottom have different parameters. They're analyzed individually, whereas on the top, they're sharing the same parameters at the same time. So what this tells you, if this is much greater than 1, then your evidence for looking at the data sets together is higher. You'd prefer to see them in the same room rather than be different phenomena, different parameters. Whereas if R is much less than 1, this is telling you tension because you'd rather say that your data sets are different physical parameters and a different phenomena. You don't want to look at them at the same time. Another way to think about it is your confidence in A goes down when you see B. They're pulling away from each other. So that's what this can tell us tension and concordance. But there is one caveat for R. And to understand that caveat, I first want to quickly double check our prior and posteriors here. So our prior is just our previous knowledge before doing an experiment. For example, I think tomorrow has a certain percentage chance of rain. Or I think my stellar mass, my lensing analysis should be between like 1 and 10 solar masses. And our posterior is what we get after we do the experiment. What do we learn? Here, if you've got just one parameter, that's going to be some kind of curve. You've got your inference with some kind of error, some standard deviation, and you've got a probability density. If you're looking at the relationship between two parameters, you're going to form a contour space. And I'm going to show you a bunch of corner plots soon, and they'll look just like this. And here you can see the inner region is the 1 sigma, and you go out and you get further ones. It's like what we learned in geography with the contours of the maps. And here you can look at the relationship between parameters themselves. And with this in mind, let's have a toy problem. Let's say I've measured a parameter for my two experiments A and B, and these are those posterior curves that I get. My entire prior range was this to begin with. I confidently said they could have been anywhere in this range. And these data sets have a very tiny overlap. I should not be very confident that they're in agreement. They want to be at different places in this parameter space. So when I calculate the R statistic between them, I get less than 1, only 0.06. This tells me that I have tension, and this is kind of what we see visually as well, which is nice. What we find is if we were to just increase our prior range, make it much wider than before, and our A and B curves don't actually change shape, they should look smaller because we've extended the range. They still have the same absolute amount of overlap, but now we have R that's much larger. So there is a prior dependence, and this isn't a bug, it's a feature. Because if I thought that my data sets could have been anywhere in this range, then seeing them so close together, that should actually give me some confidence that they are in agreement here. But what this means is if you're reporting sigmas of tension to the community, and your tension is dependent on these kind of choices you made earlier on, it can be maybe hard to communicate that and hard to make sure everything's on a same playing field. You want to be as objective as possible here. So what you can do is you can take away the prior dependence. You're going to turn your R into something else called suspiciousness. It's a great name for it. The first thing here is you quantify something called the Kullback-Leibler divergence. What it means is the information you gain going from your prior to your posterior. If your prior is massive, and your posterior is this tiny little sliver curve, you've gained a lot of information. You've said it could be anywhere here, but instead you've got that nice tight posterior right there. Now, if you put all these together between your individual analyses and your joint analysis, you get the information ratio. The reason this is a cool term is because if you subtract it from R, you get what is a prior dependent quantity. If I increase my priors and R goes up, increasing my priors should also make I go up by the same amount. So if you subtract them in log space, then you get this nice thing that should not change at all. Now, S no longer has that nice strict Bayesian interpretation of a betting ratio, but if S is much less than 1, you have tension as before. If it's much greater than 1, you have concordance. And if it's really big, you have what is called suspicious concordance. Your data sets be too much in agreement. With just normal amounts of noise, you'd expect them to be a lot more varied. So this actually gives you more information. It's a probe as well. Now, with that suspiciousness, you can then convert it to a sigma level of tension, which are the numbers that we like to report and use. And now we're going to apply this to real data for the dipole right here. Now, I talked about these data sets before. This is the NRAO VLA Sky survey done at 1.4 gigahertz. And we have the rapid ASCAP continuum survey at 887.5 megahertz. Specifically, this is the RACS-1 observations right here. And we compare these to each other, but we also compare them to infrared selected quasars. This is from the WISE instrument, the satellite. And we have the CatWise 2020 catalog. It was observed at the W1 and 2 bands. And by selecting, the way we select the quasars from other objects that are close to us, like stars, that we wouldn't want to test this with, you do a certain color cut in the space. And this is the one that's been done throughout the literature. And of course, we compare these to Planck, the CMB. Do these agree? The golden question, do they agree with the CMB? And what we can see straight away, just qualitatively as humans, is this very different structure right here. We'd like to see the nice CMB dipole in the bottom right, but instead of these other surveys, you see these very different patterns. Looking at NVSS, if you squint your eyes, maybe you can kind of see that dipole in the source count, but there's other structure there. Looking at RACS, there's some kind of vertical up-down structure there. And CatWise, we have these two big purple splotches. That's a quadrupole, so we have higher order signal as well. So there's going to be some amount of tension here. Now the gray regions, these are our choice of mask. We've masked out the galactic plane because that's spurious source emission. That will not be nice densities that is testing the cosmological principle there. And there's other small gaps as well. NVSS can't observe that far in the south, and RACS can't observe that far in the north. So those around the southern equatorial poles. Now, one final thing to note before we move on is the source counts in these surveys are very different. If you have a lot of source counts, a lot of information, you'll get a very constrained inference. NVSS has around 350,000 sources. This RACS cut has around 450K. CatWise, however, has 1.6 million. So kind of going clockwise, skipping Planck, you can imagine we have less constraining power all the way to more on our inference. And this will come up very shortly. So what do we actually get? This is a corner plot from before, and this is what we get for Planck. The reason we rerun our analysis on Planck is because we need to get the Bayesian evidence for our analysis, even though Planck has been analyzed a million times before. And we can see this is a very, very small stereo right here. So instead, we're going to replace this with just the CMB star to compare to our other surveys. And what we find is, firstly, with NVSS, with the 1 and 2 sigma regions, it pretty much agrees out to 2 sigma. Maybe you could say it disagrees to 2 sigma. And in any case, just qualitatively, you'd expect, okay, there'll be about a 2-ish sigma tension. If you continue on to RACS, you can see, okay, that's a lot further away from the CMB star. Let's extend that to 3 contours. And you can see, okay, that's now approximately just encapsulating that star, maybe 3-ish sigma tension. And then for CatWise, well, that is a very small stereo right there. So we have to extend that all the way out to 4 contours. And even then, it doesn't fully encapsulate the star. So we definitely have around 4 to 5 sigma tension. And this is just qualitative for us to get an idea about what these surveys are actually telling us. We can see that it's mainly the velocity, the dipole amplitude that we're inferring, that is higher for all of these surveys right here. And that, again, is what we expect from the literature, but based on cosmological principle, we would not expect that. Now, looking at the actual tensions between them, here is a node diagram. We're going to draw these red lines between little dots on a corkboard right now. Between CatWise and Planck, we find of our suspiciousness analysis, we get over 5 sigma tension. And these error bars I'm showing here are very generous. These are 2 sigma error bars rather than just 1. And this corroborates the results in the literature that also find 5 sigma tensions with CatWise. But rather than doing it in a frequentist analysis, we have done this in Bayesian, and we find a similar result. So this tells us that across your methods, you're going to find strong disagreement with Planck under this interpretation. Now, looking at the radio surveys, we have maybe a bit of a different story. NVSS is around the 2 sigma range, RACS around the 3. So there's some amount of disagreement here, but it is less. And you can imagine that these stereos are much larger in the parameter space. There's less information here. So we infer different amounts of tension. Now, we don't just want to compare this to Planck. Our tools can do this between all the data sets. So let's compare what they say about each other. And when you do this for CatWise and NVSS, you find that they're in no tension. 0.4 sigma. This is a strong amount of agreement. And this tells us straight away that systematic effects are disfavored. So if you look at objects, if you look at data sets being in disagreement with Planck, which is our golden data set, you might say, okay, well, what's wrong with the other data sets? What don't we understand? But this argument of systematics goes away with this, because catwise is in the infrared, NVSS is in optical, in radio, and ground-based versus satellite-based, completely different systematics. This is telling us that there's a common astrophysical signal causing this dipole here. Now, RACS, however, you cannot say the same about it. Instead, it seems to be in moderate to strong tension with everything else. So that argument about systematics might then apply here. Maybe there's something inside the RACS catalog that is affecting these tiny source count modulations that we don't yet understand. And this isn't telling us that there's any problem with RACS. It's telling us that we've chosen to do the tightest possible test of any source counts on a survey, and that maybe we're getting something that we don't yet understand. See, these radio surveys, there's all these different things that can affect the source density. You have ionospheric fluctuations changing the temperature, and you do flux scaling to compensate. But that is a change in the source density, even by a small amount, and we're sensitive to that. We're sensitive to your resolution. Radio sources are complex, they're not just single, you've got multiple, many at a time. And if your resolution is different, you're going to get different inference across the sky. But you can convolve all to the same resolution to try to account for that. But essentially, modeling these systematics and understanding them to a T is the future for working with data sets like this. Because for around 20 years, when this test was first theorized for the cosmological principle, we didn't have the source counts to do it. And now we do. We have to understand those source counts. And speaking of understanding the source counts, they are also going to affect the amount of information you have for inference. Now, I've said this a few times, and I wanted to then actually test this using simulations. So I first start with a sky where I put the same number of sources in every pixel. It's all the same color. And then I input some kind of dipole into it analytically. And then I do a Poisson draw. This is a Poisson point process, putting in my shot noise. And I'm going to repeat this for 50,000 to 50 million sources across my surveys and see what happens. And I'm going to do this with a few different dipoles. I'm going to first insert the one from NVSS or RACS, which is our radio dipole, you could say. And I'm also going to insert the same one from Planck. And then I'm going to compare both of them to the Planck data itself. And you might kind of see a redundancy here at the bottom, which is if I'm comparing a Planck dipole to a Planck data, I shouldn't get any tension. These are the same thing. And this is what I'm calling my CMB dipole simulations. And the ones at the top, well, they should be in tension because I'm comparing radio dipole to that from Planck. So here we have the red and the blue as our color coding for the next slide. And this is how the tension evolves with the number of sources. So the y-axis here is tension in log space. The higher you go, the higher the tension is. And then we're moving towards higher source counts on the bottom. And what we find is that the CMB dipole ones, the blue ones, they're very consistent. Doesn't matter how much you change the number of sources, you're getting very low tension there, kind of plateauing and oscillating around the 1 sigma range. But then we see of the radio continuum dipole that we have an increasing amount of tension here. And this makes sense. Your dipole is centered at some different place in the parameter space to Planck, because these are the radio dipoles. And if I increase the number of sources, my posterior is getting tighter and tighter, becoming a really small little dot, and that is more signals, more tension away from the CMB expectation. But what is very interesting is that at low source counts, the blue goes up and the red goes down, and they converge together. And this is an effect of shot noise that we're seeing. Because when you've got no sources to work with, your parameter space looks like eggs. It's this big unconstrained posterior taking up all the possible options. And if all the possible options first came from the red simulations or from the blue simulations, they're going to look the same. You can capture the entire parameter space, but you start with a Planck dipole, the entire parameter space, you start with a radio dipole, you can't tell them apart. They look the same. So here we see it actually plateaus to some kind of characteristic tension for this problem, which happens to be around 1.6 sigma, which is interesting. Now, the error bars I was showing here are the 2 sigma range, because I repeated this for each source count 100 times. So I get heaps of different realizations of the same problem, of the same noise. And that means that these are actually probability distributions. So we can take these 3 cuts and turn them on their side and look at those probability distributions. And this is what we find. So again, we have those 3 cuts at 50, 500K, and 5 million. And this time tension is now on the x-axis. we're seeing how probable is to find that amount of tension at this number of sources. And what you find is that at low source count, there is this huge overlap between the two distributions. You can't tell them apart. That's what I was saying before. Now we're seeing it seen in probability space. There's a huge degeneracy here. So if you get a tension measurement from here, you don't know where it came from. Is it tension? Is it concordance? You can't make a conclusion. No inference. Whereas here, about 500,000 sources, which is about the amount that we're using in our radio surveys for RACS and NVSS, you find that there's still significant degeneracy in the middle. If you get a tension between that 2-ish, 3-ish sigma range, you again can't tell whether it's actually concordance that just happens to look bad because of the noise in your experiment, or if it's actually tension that you're recovering. And this is around the same source counts we were using from before, again. But if you go to the future, with many millions of sources in your catalog, you find these distributions move very far apart very fast. That means if you get any tension in this valley between, you'll instantly know whether you've got concordance or tension. And this is what we're looking towards in future surveys. If you were to take the experiment that I showed you just then with the simulations and assume an NVS dipole or RACS dipole, you only need about 10 to the 6 sources. And given that SKA is going to observe many, many more of that in radio, we are very much on the cusp of untangling this. And we can't just look to SKA. We also have LSST, Euclid, SphereX, and even current surveys that are still being completed, like EMU as well. And all these are more opportunities to get more sources. And that gives you more information, so I want them all right now. But we're looking towards the future. And as part of that look towards, we want to quantify what we can get. And myself, as part of the Sydney Dipole group, we're working on quantifying that. We're taking mock observations from the SKA team, inserting dipoles into them, and seeing what can we get out with different amounts of sky coverage, different amounts of sources, different masks as well. And what this is telling us is what to expect when we actually get the SKA here. I mean, the timeline for it has been moved down a bit, and that gives us more time to quantify what we expect to get and how we can use it straight away. And that's part of the dipole chapter of the upcoming SKA science book. And I talked about EMU, which is something that's maybe a bit more close, and it's happening right now. And here we have many different little pointings in EMU that are being tessellated together. And when we think about dipole inference, some people might assume that you can't measure the dipole if you don't have the whole sky. But I'm here to tell you that you can. If you just get a small patch, like in that top panel there, and I have a number of sources in that small patch, I can measure a dipole if there's a lot of dipole gradient across it. You can see in that patch, I had a big gradient between yellow and purple right there. If I move that patch across the sky, I get different inference. What this bottom panel is telling us that if I move the patch towards that kind of equator, the S shape of the dipole modulation, I can infer a dipole. But if I move it towards the 2 poles of the dipole, those purple areas, at those poles, it just looks like a monopole in that patch. There's no gradient there, so I can't infer a dipole. So little patches are good. You just got to think about where you're putting them and which ones you're using. But it's always the case of more sources is better for this. For your sources, you get more bang for your buck if your patch is in a better spot. So with EMU, we're going to get many sources, which is way past the threshold I talked about before by 10-fold. But even with the current number count, that is still way past the inference threshold for a dipole. So it is down on my, it's on my to-do list. Once I get to it, it'll be EMU time for dipole. Now, an elephant in the room might be, are we actually measuring what we think we're measuring? What about local sources towards us? In NVSS and RACS, we cross-match and remove sources out to 0.1 redshift, and that is past the theorized transition to homogeneity, which is only 0.025. And we found that that reduced the dipole amplitude by 10 to 15%. And ΛCDM does predict, local clustering of sources, but compared to a primordial dipole, our dipole from our inference, you'd expect them to be different orders of magnitude. The general consensus is that local sources that still might be in the survey due to incomplete cross-matching and limited redshift surveys, that generally can't explain the greater than 5 sigma tension. It likely explains some of it and get it down a bit, but 5 sigmas is a lot to get down. And we, again, saw it only was about a 10% decrease in the amplitude there. So putting this all together, maybe it's a bit more philosophical. Like, we thought the universe should be homogeneous and isotropic. That is only one way it could be. If you have to break that symmetry of the universe, that isotropy, there's infinitely many ways to break it, like cutting up a sphere. And it could be anything else apart from this. Some solutions to the dipole tension would be, what if we're in a large dark matter supervoid? Let's say the void is 3.4 gigaparsecs, which is massive, and you're just 300 megaparsecs from the center. That would distort the observations you see of sources around you, and that could solve the tension. That is quite a significant and contrived thing to be in, us in the supervoid. And by the Copernican principle, we don't think we're special. But again, it's something we might have to give. It could be that sources have an inclination towards evolving along a certain direction. There is actually more in a certain direction of the universe. That would be anisotropic, non-Friedman, and again, that could be it. But it could be something entirely new that we haven't even come up with yet, or can't be explained this simply. So looking towards the future, myself, as part of the Sydney Dipole Group, have got a range of projects going on. I'm looking to quantify these tensions using machine learning between models, which allows for a different method for prior calibration, which means you still get a nice Bayesian interpretation without turning it into suspiciousness. And I'm also looking into the radio systematics. My colleague Oliver is looking at the infrared. Bassett is comparing different approaches. You've got frequentist versus Bayesian. And what I said before about the universe maybe being anisotropic, being a solution to this tension, well, Jordan's looking for that. He is doing simulation to see what dipole inference changes when you have a different universe that you're looking at. And we're working on that SK dipole book as well. So in conclusion, we have Hubble tensions, we maybe have S8 tensions, but we definitely have dipole tensions. And it does appear to be one of the most significant ones that is still plaguing ΛCDM. And the data set tension analysis here does corroborate the results of literature, the 5 sigma tensions, but we've done it in a different approach, and different angles give you the same result, which is nice in a way. And looking at NVSS and CatWise, we have a strong disfavor towards systematics, which is very interesting for those arguments that say that it could be systematics causing that. But then again, that same argument for RACS showed that moderate strong tensions do everything else, which tells us we have to look deeper into it and understand what's going on at the source count level, which is my next priority. And finally, looking towards the future, all these surveys with the huge amount of source counts as we go into an age of even more precision cosmology is going to be the next answer to this question. Do we have a strong argument against the cosmological principle, or is it systematics and short noise? Thank you.
Wonderful. All right, questions? I have now someone get in. Miro, jump in.
Thanks, fantastic talk, really. This is a sort of inspirational type of talks. I have a comment and a question. The first comment is, we know that there is a huge dependence of a number of radio sources versus the frequency. So in that sense, I'm a little bit worried comparing NVSS with the RACS. That is on a log scale, it's actually very significant. What I'm saying is you should see significantly more sources in RACS because RACS frequencies are lower than NVSS. So what we know is that most of the sources, radio sources, are of non-thermal origin. I'm talking about the background, talking about the sources, faraway sources, let's put that way. We know that that is about 3-to-1 factor. But going to a lower frequencies, that should be even more pronounced. So I think you may have a bias there. I'm not sure. I would like to hear your comment on that. But my question is, why you didn't use the NWA? NWA is a very much complete catalog. Yes, it's not that sensitive, but it should also give you some ideas and should be a part of this comparison. Once again, well done.
Thank you very much. There's a lot there, which is very interesting food for thought for me. Well, the first thing that comes to mind about MWA is my long list of about 50-ish data sets that we want to look at for the dipole tension. It is very much on that list. And I'd agree it would be interesting to compare, especially to NVSS and RACS here. Putting any of these, whilst the machinery used to do this dipole inference can be used for any of these data sets, you need to understand how the source count is going to affect your dipole inference before you do it. you kind of want to have your measurement blind once you get it. You don't want to mess with the data too much after that, which means that the time spent to put in the mask, think about cross-matching, think about perhaps a different form for the likelihood function, the inference, that takes a lot of time. So it's on the list of data sets to do, but it may take many months for that one and the ones before it.
Can you comment something about the expectations of a number of sources versus the frequency? I think, this is a very dangerous game. If you go back to your slide 20, very quickly, this slide where there is errors of 4 different surveys, NVSS, RACS, WISE, and Planck in the center.
Yeah.
If you go back to that slide, you have... Oops, sorry, I think, we lost your slides.
Is unusual. There we go. Sorry.
Not that slide. The slide where you have the circles with the Planck in the center and the 3.
Yes. The tension diagram.
Yes, the tension diagram. Yes, that one. So I have a strong reservations about this NVSS to RACS. As I said, you are comparing something which is a significantly different frequency. And that difference between 1.6 and 835 or 834 or 884 is significant enough that will not be fair to compare at all. As I said, you expect to see far more sources in RACS because average source would be a very steep radio spectrum. So I'm really, I don't know. I don't like this comparison between NVSS and RACS for this particular study. So, I hope you understand my point. I'm sorry,
Yeah, and this isn't a direct comparison of one catalog to another, and at different frequencies, you'd expect to see different objects, which is what you're saying. And as you go to
exactly
high frequencies, the magnitude of those objects increases, like the number of them.
Yes.
But if you have a low number of sources in one survey and a high number in the other, you just expect the effect of shot noise to be different here. So perhaps your inference of the dipole will get worse if less sources. But because that dipole is where the kinematic interpretation is just an effect of us being an observer, it shouldn't matter what objects you're looking at, as long as they're at cosmological distances. You should expect to see the same kinematic dipole imprinted on those objects.
Well, yes, that's correct. If you have sources which are uniformly distributed in various spaces. What you have here is, it's not uniformly. As I said, it's a 3-to-1 ratio of the non-thermal steep spectrum sources versus the other ones, which will actually introduce you a systematic error at some level. So I think, this 0.3 sigma error is a much higher. That's what I think at this stage. I understand what you're saying. I'm just trying to say it's not that simple.
I have a question for you. That 3-to-1 difference in the types of emission, would you not expect that to be the same at any given point on the sky?
That's correct, yes. So we did these studies, actually Ray Norris did this study in his pilot, which I think it's one of the best studies, but we did this in several other fields, LMC and SMC field, when you clear your foreground sources, Magellanic Clouds or galactic sources or whatever. And then you see a bump of a significant number of, which we call the thermal, a flat spectral index sources, which are not insignificant.
Interesting.
And I can show you these plots. If some of my students are there, probably they can point this to you today. I'm sorry I can't be in today, but it is something that we've seen in a number of surveys.
That is interesting. It'll be interesting to see if I could modify the likelihood function, count that systematic, and then see how the tension evolves.
Excellent. Yes.
This relates to something I'm working on at the moment, which is accounting for any kind of systematic in your survey. If it's something very nice and linear with declination or with some other coordinate, that's easy to model in the likelihood function. But if it's something more complicated, like an Eddington bias or a bias for a certain type of emission or something, that might have an intractable likelihood function you can't write down. But in that case, you can move to simulation-based inference. And that's where, as long as you can simulate the systematic, which we absolutely can in a mock sky, then you can get a neural network to learn off of that and then give you this likelihood function that would otherwise be. So
I can tell you definitely that we can simulate that, because wherever we looked, I think we looked in 4 different fields.
Yeah.
We see the same results of behavior of spectral index, radio spectral index across the very large bandwidth.
Yeah. Thank you.
Good. Thank you.
Yeah. Lawrence.
Hello. Thanks for your talk.
Data scientist.
I just got a few questions that wasn't clear for me anyway. At the start, when you were talking about calculating this tension, you said you're calculating the probability of the data. So it was the likelihood of the data was, yeah, so it was one of the earlier slides.
Yeah.
Yeah, so these Zs. So these are the likelihoods. What are these the maximum likelihoods, or were you using some other parameters for the model that you're getting the probability of?
So here, the Bayesian evidence is the marginal likelihood. So it's that integrated across all the parameter space for the model and integrating the entire chain.
Okay.
Yeah.
All right. And later, when you're using the Kolbeck-Leibler divergence, does it matter that it's not symmetric? Because I couldn't see that there was one.
Yeah.
Like,
Yeah.
how do you deal with that?
Yeah. So it is not price symmetric. It's not symmetric. You get different results going each different way. Absolutely true.
Sorry. Yeah.
Expand it. What do you mean? Not symmetric?
Oh, sorry. The Kell divergence is looking at one distribution to another. It's comparing them. It's looking at their match and mismatch. And if I compare my prior to my posterior, it's like that, yellow versus blue. If I compare posterior to prior, those will flip. So it's not symmetric either way. You can imagine, because it's a very simple way it's written down, you could just account for that, like raising it to a power and flipping it or something. But this is just an approximation. The equation is actually a bit longer than that, some integrals. I haven't looked at how you could form a log I, an information ratio, with the KLs the other way. But I assume it could be derived. I've only seen the information ratio constructed with the KL in this direction.
Okay.
But if you reverse the direction, because you're still dealing the same prior and the same posterior, you could probably derive how to make an information ratio that captures how R changes with prior. But you just need to change the form of it. But I think you could make it with enough reworking.
All right. Thanks.
Yeah, you have to make sure you're doing it in the right direction for this ratio to work as it's written down. Yeah.
Thank you.
We'll go to Bob.
Yes, thanks for the lecture. And I actually did understand a bit of it. But from a non-astrophysicist point of view, what is the significance of such a tension? What does it mean in terms of astrophysics besides being an interesting thing?
It would mean that something as, well, I was going to say something as simple, but something as important or fundamental as a metric that you can write down to describe, to be a solution to Einstein's equations and describe how gravity should change, how the curvature should change. Something as simple as that would require a new solution and wouldn't work under a non-Friedman interpretation. Like under something that would solve perhaps the dipole tension. So there's not many solutions to those equations. So that would be a major problem. That's just one example. But maybe more fundamental is we like to think that we're not special in the universe. And if the universe were either not homogeneous, like we're in a void, that would tell us that maybe we are special. That would be strange and interesting and very much question what we like to believe. Having a universe that evolves in a certain direction, maybe how we're placed relative to that direction and angle, that could make us special or not special. It kind of puts everything else on its head, all of our fundamental assumptions. If anything, it might bring us more to something that's more geocentric, which I'd never hear myself saying. But yeah, that's what I think.
Thanks.
Right, so it's just heresy, that's all we have to worry about.
Yes.
Nick,
Yeah, the IAU Inquisitors will be around in the morning. Nobody expects the Astronomical Inquisition.
Exactly.
But so you've got your long list of surveys, which obviously you're planning on working through for the rest of your life, I presume.
I'd love that tension diagram to be
yeah.
bigger
Yes.
and then
more
through,
corners.
and then like in all dimensions 3D. But then have a different diagram for each different model you could do it, because it's all, you know, the lines depend on the model. So just
Yeah, that's
eventually make it bigger.
so you're going to start doing 3-hour talks.
Yes.
But so obviously those are surveys that people are doing and you're going to grab them and do what you can with them. If somebody, not me, wrote you a blank check and said, what survey do you want that's going to do the best possible job for this? Any wavelength, any instrument, what would you ask for?
I want SKA now.
SKA?
Yeah.
Okay,
Yeah.
so you've already got it.
Yeah.
You just need SKA to work right now.
Yes, and there's only so much money you can throw at something to make it faster, I guess. But my reason for wanting that now is that the challenge against the standard model is already quite strong in the infrared with the quasars, but that same challenge cannot be said for the radio surveys. There's less sources, so the tension is lower in any case. But each survey individually is in a low tension with Planck in comparison to catwise. But even they get up to like 3-ish sigma. Now, some people have pulled together these radio data sets and analyzed them all at the same time to claim one bigger significance. But you can't necessarily combine data sets like that if they're in tension themselves, which is what this shows. So what we'd like is one big individual survey. And to me, SK is one of the best answers for that.
If I can. So comment first. So MWA is probably not so useful to you because from memory, it's probably capped at about 500,000 sources, and that's including galactic plane. So once you start filtering it out, you're going to lose your source count very, very quickly.
Yeah.
Do you have a feeling on how many sources you filtered out of RACS though? Because some of the newer RACS iterations are at about 3.5 million sources, I think.
Yeah.
But that's including galactic plane as well.
Yeah. So the original RACS 1 catalog, I think I had like 1.8-ish million. I can't remember the exact number, but that means we probably took around 1.5 million off to make this current cut. Specifically, we use a flux density cut between 15 millijanskis and 1,000, and then we mask galactic plane that much. Yeah. But if there's a cap on the sources with the galactic plane for that survey, that would make it difficult. If one at the time would still be worth perhaps looking at it, because if anything, it would just tell you that there's maybe no constraining power in the inference, but it probably wouldn't tell you like less sources wouldn't give you an incorrect result necessarily.
Yep.
It's accounted for.
The other question I've got is how much does human bias come into this?
In
So
what
I
way?
know when preparing catalogs, the first thing you're doing is you're comparing with like positions of a different catalog. And any that are spurious, you tend to throw out, regardless of whether or not there is evidence to throw them out. We don't have evidence to say that this is actually, positive or negative. So to get it published, you will just cut it.
It's the process.
How much, and this may not actually be answerable, but is it possible to quantify how much of an impact that could have?
So that is essentially what I'm going to be looking at with RACS, try and look at the entire pipeline. I'm working with Emil Lenk and Stefan as well on that. So I want to get under the hood and understand all those processes. Since I haven't done that deep dive yet, I probably can't answer the question right now, but I'd like to think that any process that happens there, including one that's a more human process, by understanding it enough and perhaps modeling that, then we can quantify it anyway. If I can simulate it, it will work here. Yeah.
Cool. Thank
you. Students, any questions from students before Miro has another blast?
Yeah, I had a question.
Yeah.
One of the things that I saw, I think, was the main thing was the catwise AGN ones that was causing the major discrepancy.
Yeah.
That seems to be on the low infrared cut. How confident are we that that's like only getting AGNs? Like, how important is that to the thing? I don't know enough about AGNs to say that, but it seemed to be based on sort of one infrared cut. Is there any cross matching that could be done there or anything?
Yeah. So specifically, whether that cut just selects AGNs, I'm also not a huge expert on those particular sources either.
Milliquas is a cut specifically of infrared AGN that has been cross-matched with all of the different surveys to confirm as much possible AGN.
Right. Okay, there you go. The one thing to add, I think I do remember that the main paper that came out saying we have a big tension, we've used catwise to look at this, they used that color cut from the literature, which was well motivated as well. And I think they also did a lot of cross-matching with the catwise sample to Stripe 82 and other regions to check the fidelity of the quasars. I think if there were big holes in the justification of if they're quasars or not, that I probably would have read on that a lot, because it would be tearing, people try to tear the paper apart in ways. So based on not hearing that, perhaps I think it's okay. But what you said. Yeah.
I'm going to jump in before Miro. So suppose there's lots of options of what this could be, but suppose this is an intrinsic dipole in the universe somehow, right? And we're also moving through the CMB. So there's sort of two dipoles there. Which one is it just the biggest one that Planck sees, or does it get confused and look in the middle? Or so how do you, I mean, there's sort of multiple there are real dipoles right, because we are moving, presumably. Yeah. Like how much does that fact sort of ruin it to find an intrinsic one behind the scenes?
Yes, if we have a dipole in the universe and we have a motion dipole, explaining what Planck sees for that one dipole, I have no idea how one would then do that. Right. But you can absolutely run a double dipole model. It's not directly the same as a quadrupole, because quadrupole you have two unit vectors. The dipole you can have two vectors as well. It's minutely different. How it would look, I have to model it. I have to run the simulation, put two different dipoles in. But people have tried to do something called quantifying the clustering dipole. So maybe there's some clustering dipole from ΛCDM, and you have your kinematic dipole. And can you compare both? Can you let your inference just test all the combinations? And what you find is two dipoles, there's a significant degeneracy between them. Right. But what you can do to break that degeneracy between them is you can fix one in either amplitude or direction. So if you fix one to the kinematic dipole in the CMB direction or amplitude or both, then you can let the other dipole wander and see what their superposition would be. And for those, you can then compare, are they even the clustering dipoles the same across these data sets? But that's where my mind goes to. Okay, so yeah.
Good. All right, Miro, hit it.
Yeah, it's one more warning about comparing things, and that is between the infrared and the radio. Ray Norris discovered the sources which he calls infrared faint radio loud sources, which also contributes a lot to a proper comparison between the infrared and the radio. I forgot, I don't know on top of my head what's the ratio, how many of these sources are there, but I remember a significant group of radio loud sources are there, and you won't see any infrared source there, which may further influence your statistics there, your completeness there in that space. And just another final comment, yes, please look into Millikan's. That will be very interesting. I don't know how many sources are in Millikan's catalog, but I think you can do this actually, in probably a half a day and check what kind of distribution you see there as well. So another point, please be careful in comparing the infrared with the radio as well. Okay.
Yeah. Thank you for that. I think that effect does not have an impact on the dipole analysis here. We are aware of the difference between the radio and infrared, many radio sources that are loud and not loud in the infrared as well. The only limitation here is that if you're trying to cross-match with a redshift server that is optical and infrared, and those components won't always match. So you don't have high fidelity cross-matching, but the distribution of those complex radio sources that are not loud in the infrared, we still expect them to be distributed the same way everywhere under the cosmological principle past a certain distance. And based on what you know about these sources themselves, you can infer the redshift of the population. And again, if you're doing a one-to-one comparison of about every single patch of the sky to catwise and to a radio survey, then you'd find a mismatch that would be a systematic, and then your analysis would make no sense. But if you're looking at the population overall, you just find that it's overall more thinned out. Depending on which continuum you're looking at. It doesn't introduce that kind of bias.
So you are actually not necessarily interested in sources that it's seen in all frequencies. You don't care about that, do you?
What would I care about then?
Well, I thought, that's definitely the sources that, you know about them. And the one which pops up in one frequency and don't pop up in another frequency, you don't want them. Well, that was my assumption. It's obviously wrong assumption, right? No?
As long as you can test it at one frequency itself, it's fine. If they don't appear in other frequencies, that's also okay. I guess what I care about are the objects. And if I only see some of them, if someone's turning off the lights of some objects at a time, that's fine. If the lights aren't being turned off homogeneously across the sky, then that's not fine. That would throw off your analysis. You have to model it. But as long as any selection effect like that is the same everywhere, then it is okay.
Good. All right, we've hit time.